We're going to finish up chapter 8. Just to remind you, we are going to do Bohr's theory, quantum mechanics, wave-particle duality, and then we're going to work through some information about the periodic table. So Niels Bohr was a younger scientist. He actually visited Rutherford's lab and was inspired by what Rutherford was doing in his research. And so then he later developed his own theory, which was centered around 3 rules. The first rule was that electrons can only exist in certain allowed orbits. They can only live, meaning in these orbits are these shells, and they can only live in specific ones. They can't just pick anywhere. Within that orbit, the electron does not produce any sort of radiation. So it's just hanging out in its shell, in its orbit, revolving around the nucleus, but it's not going to produce any sort of radiation while it's there. However, when an electron changes its orbit, so when it goes from one shell to the other or back, it then could either emit or absorb radiation. So it's a very specific situation where if it's going from a lower to a higher orbit, so going up, it's going to emit radiation. When it's the opposite, it's going to absorb. When the electron is going from a higher to a lower orbit, this is when it's going to emit radiation. And sometimes we see emitting of the radiation in the form of like fluorescence, so like lightning bugs, glow sticks, things like that. That's when the electrons are falling back down. Now there is a term used to describe these levels, and the lower orbit is always going to be called the ground state. It's the lowest energy orbital, but it's also going to be the ground state. The higher energy orbital is called the excited state, which is why it's going to take energy to get that electron up into that excited state orbital. Now, there was a problem. Bohr's theory only explained atoms that had one electron. And the only element that we have on the periodic table that has one electron is hydrogen. Everything greater than that helium and up is going to have at least 2 electrons. So because it did not work for atoms larger than hydrogen, it meant that we needed a new, better theory to come along. So there were some further experiments established that basically confirmed that there is a wave-particle duality of light and matter. So remember when we talked about light in chapter 7, we said that really light behaves as a wave, but it also exists as a particle. So it's both. And electrons are going to be the exact same way. It's going to be a particle, but it's going to behave like a wave. So this wave-particle duality was really confirmed by a scientist named Louis de Broglie in 1923. So just a little bit after Niels Bohr established the Bohr theory in the early 1900s, de Broglie came along and postulated that if a particle of light can be dual-natured, then particles like electrons should also be able to be dual in nature. And so electrons, we know, are confined to a space near the nucleus. They don't just float around anywhere. But before de Broglie, we treated these orbits as pretty much superficial circular orbits, much like what we observed in the solar system, because that's what we knew a lot about the solar system. We were modeling it after that, thinking that the nucleus and the sun were very similar, the electrons and the planets would be very similar, and their orbits would be similar. But de Broglie came along and actually determined that electrons don't just travel in a linear circular path like the planets do. They actually are going to travel in what we call a standing wave. So the red line here. So if I were to break this line in half and maybe straighten out the line, what we would see is it becomes a wave, just like light. And so what this means is that electrons are dual in nature, and they don't obey by traditional applications of the solar system. So therefore we have to apply something a little bit more complicated, which is this wave-like nature. So what this brought to us is what's called wave mechanics, and it's a very complicated topic. But what's important for you to know is here on the slide. It was developed by a scientist named Erwin Schrödinger. It treats atoms as three-dimensional sets of waves. So when you hear three-dimensional, you have the z-axis, the x-axis, and the y-axis. So all three dimensions, instead of treating it like a two-dimensional circular wave, we're going to let it be three-dimensional. With wave mechanics contains successful ideas of Bohr model and much more. So wave mechanics is still built on Bohr model, but it has to be expanded to accept that there's this complicated nature of electrons, that it behaves like a wave that Bohr model didn't account for. This particular theory does describe the behavior of hydrogen and also all atoms that have more than one electron, which is what Bohr's theory didn't quite get right. Now, wave mechanics forms our fundamental understanding of chemistry. It is a very important concept in chemistry, but it's beyond the scope of this class. You normally don't learn about wave mechanics until you're in high school. But this early history timeline is something that you would teach at a lower level. Even though you're not going to teach the complicated concepts, you're going to teach the history and the discovery of science. Now, these right here, these are these three-dimensional systems I was telling you about. We have the s orbitals, the p orbitals, and the d orbitals. And we'll see in a couple of slides how these orbitals are clearly laid out on the periodic table. Another way we could classify and organize our periodic table. So this is the periodic table. This is up to date. It has all of the 118 elements that we currently know exist. Anything that's beyond, gotta find it, element number 82, right here. Anything that's above element number 82 is considered to be radioactive. So we have ones we know like uranium. Bismuth is used in imaging, medical imaging. And there are some few exceptions of elements that are radioactive, like technetium is used in bone scans. It is an exception to the fact that elements 1 through 82 are not radioactive. Technetium is. But all of the elements on the periodic table are organized in a specific way. Now, what you're going to do is you're going to go back and you're going to download the blank periodic table version, and we are going to label it and write down all the good information that we need to know about the periodic table. So go get that, download it, print it. However you need to do that, you'll need to have colored highlighters, pens, some sort of way to clearly distinguish these things that we're going to label. I'd recommend probably 10 colors if you can find them.